So last time we did rectangular pulse train. Okay, the rectangular pulse train is a train of rectangular pulses, and it is symmetric about the y-axis. All right, the period is assumed to be t0 here. That is the period. Okay, the height of the pulse is assumed to be v, and this signal is called xt. All right, the width of the signal, though, the width is just t. All right, the width is not t0. You have to differentiate between t and t0. T0 is the period where t is the width of each pulse. Now we found that for this rectangular pulse train, the Fourier series coefficient starting from C0 is found to be Vt over T0. In other words, C0 is the average value. This is the average value, which is C0. Okay, if you think about it, C0 is the average value of the signal. So I'm just gonna write it down. This is the average value of xt, or sometimes we call it a DC offset or DC component. It is the component of the signal where frequency is zero. The zero frequency component. And Ck was found to be Vt over T0. Okay, and the function is sinc function of K. Oh, sorry. K omega naught T over 2. Right? And these are the Fourier series coefficients for all K. And omega 0 is 2 pi over period. Now, the sinc function has been addressed in the first chapter. Okay, though I think I should say something about it. The sinc function of x at x is defined to be the value of sine x over x when x is not equal to 0. And it is defined as number 1 when x is 0. Okay, this is a sinc function. Now, the reason why I bring sinc function up is because we will see sinc function a lot when we study Fourier transforms. So it will come up a lot, especially in communication systems. So we should know something about sinc function. If you plot the sinc function, okay, if you plot the graph of a sinc function with respect to x, okay, the graph will look like this. Graph of a sinc function looks like this. And if you look at the envelope of the sinc function, it will be like a hyperbola. I think I shouldn't write it so down. Right. This point here is where x is 0. Okay, it's by definition 1. This is the value of the sinc function at 0, which is 1. This is by definition here. Okay. And the reason that we have to say explicitly that this is equal to 1 is because by definition, when x is 0, this value is not defined. Okay, so that's why we have to specifically say that when x is 0, sinc function of x is 1. Oh, yeah, thank you. When x is 0, the sinc function is 1. The sinc of 0 is 1. Now, and this is reasonable because if you look at the sinc function, if the sinc 0 is 1, then sinc will be continuous, right? It will behave very nicely if the value of it is 1 because the limit approaching 0 from the left and the limit approaching 0 from the right will be equal, and that would be 1. Okay, and as for the zero crossings are the points where sinc is 0. We can determine those zero crossings by looking at the value of sign here. We know that whenever x is a multiple of pi, the value of sign will be 0, right? So these zero crossings will occur when x is a multiple of pi. All right, so this is the graph of a sinc function. Now, from the Fourier series coefficients here, we can write down the Fourier series of the rectangular pulse train like this. So we have the Fourier series of the rectangular pulse train as xt equal to summation ck e to the j k omega 0 t, where k goes from negative infinity to infinity. Now we can plug in ck here, and that would be summation of k equal to negative infinity to infinity, and vt over t0 sinc of k omega 0 t over 2 e to the j k omega 0 t. Okay. Now, if we unfold this, okay, if I'm gonna unfold this summation, if I am to unfold it, I have to think about each k, right? When k is 0, okay, the value of x would be vt over t0. When k is 1, then the value is vt over t0 sinc of omega 0 t over 2 e to the j omega 0 t, right? Now when k is 2, I have vt over t0 sinc of 2 omega 0 t over 2, and I don't have enough space, e to the j 2 omega 0 t, and so on. Now, when k is negative, I have, this is when k positive, okay, that when k is negative, I have vt over t0 sinc of minus omega 0 t over 2 e to the negative j omega 0 t, and so on. Oh, this is sinc, sorry. This is sinc. Sinc, not sine, sorry, sinc. Sinc. And then sinc minus 2 omega 0 t over 2 e to the minus j 2 omega 0 t, and so on. Okay, so these two are exactly the same. Oops. Okay, this is the interface series where we use the signal notation. This is the unfold of this infinite series. Okay, we have infinite terms. This is when k is equal to 0. Okay, when k is equal to 0, the sinc would be 1, right? And the exponential would be 1. So we have only this term out. This is when k is equal to 1, when k is equal to 2, and so on. And this is when k is a negative integer. This is when k is equal to negative 1, negative 2, and so on. Now, when we look at this, okay, we are trying to plot. We want to plot the coefficient here. Take a look here. We want to plot these coefficients. What? What is that? Now we're trying to plot these coefficients for each of the frequencies here. Okay, for each of the frequencies here, we're trying to plot these coefficients. Now we look at this. Okay, omega 0 to omega 0, minus omega 0, minus 2 omega 0s as frequencies. So the Fourier series of x, the coefficients will only exist at these frequencies. For example, when omega is 0, when omega is omega 0, omega is 2 omega 0, frequency minus omega 0, minus 2 omega 0s, and so on. So we plot this with respect to omega. We're going to plot it with respect to omega. This is the value ck. Now at omega 0 here, at omega equal to 0, we look at this. That is the value of ck at omega 0 is there. This is exactly where omega is 0. See, this is omega naught. Omega is omega 2 naught, minus omega naught, minus 2 omega 0. So this is where omega 0. So we plot this value at omega equal to 0. Okay, which is Vt over T0. Yeah, this is C0. Now, we have to plot this ck for these frequencies, right? So the next frequency is at omega 0, right? 2 omega 0, 3 omega 0, and so on. Now, if you use your calculator to calculate this, the values of each term here, then you can plot the values for ck at each of the frequencies here. Right? You can do that by using your calculator. Okay, you can use your calculator to plot this value for each of the ck's. But The trick to do this, okay, if you don't want to use your calculator and you want to sketch the graph, just sketch a graph. The trick to do it is to draw the sinc function. Okay, you want to draw the sinc function. You want to draw the sinc function. Sinc function. This is a sinc function. This is the same graph of this one. The graph of the sinc function. Except that this sinc function, okay, is Vt over T0. And then you plug in you plug in K omega 0 as omega. Okay, you take this one, this whole thing, this product here, K omega 0, you plug in as omega. So it would be sinc, oh, this one is sinc, sorry, sinc. You plug in it as sinc omega t over 2. So that when you plug in omega as k omega, it will give you this value. Okay, this is for all omega here, right? This is for all omega here. If you plot it, you're gonna have the red lines, the red graph. But for each of the omegas, for example, if omega is equal to omega 0, here you get this value. If omega is equal to 2 omega zeros, you get this value. If omega is equal to 3 omega 0, you get this value. And so on. So here, at this omega, you just plug in omega here equal to omega 0, right? And you're gonna get that. So I'm just gonna write it down here. Okay. Get that? And if you plug in omega as minus omega 0, and because of the even function, even property of the sinc function, right? You get the same value. Sinc function is symmetric about 0, right? And so on. So this graph is called frequency spectrum. It tells you the component of your signal at each of these frequencies. So it tells you that the component at frequency 0 is this value, is this number. At frequency omega 0, the component of the signal is this number. Okay, this graph is called the frequency spectrum. Each signal has different signals have different frequency spectrums. This is the frequency spectrum for rectangular pulse train. Okay, the signal is some other signals, then the frequency spectrum will look differently. Right, this is specific to rectangular pulse train. So this graph is called the frequency spectrum. All right. So this is C1. This is C negative 1, C2, C negative 2. Oh, and the value here is the zero crossing. This happens when omega is equal to 2 pi over t. This is when omega is 2 pi over t here. Inconsistent with this one. X has to be pi, right? X has to be pi. So this guy should be pi. And when this guy is pi, then omega equal to 2 pi over t. Okay, you got that, right? And here, the zero crossing here happens at minus 2 pi over t. And here is at 4 pi over t. And here is at minus 4 pi over t. And so on. Now, if you notice here, we are plotting omega at negative values as well as positive values. So this is, sometimes we call this two-sided frequency spectrum. Two-sided. Two-sided frequency spectrum. The word two-sided means that we are considering both negative and positive frequencies. Okay, that's why we call it two-sided. Now, sometimes people don't understand negative frequencies. The notion of negative frequencies is pretty tricky to understand. Right? We would normally say something, we would normally understand positive frequencies. So when that happens, we can plot one-sided frequency spectrum by transforming, okay, by writing the Fourier series. Instead of writing it in a complex exponential form, we're going to write it in a cosine form. Okay. Now, in cosine form, the Fourier series of this rectangular pulse frame is x of t equal to c0 plus summation k going from 1 to infinity to absolute ck cosine of k omega 0 t plus plus the phase of ck. So if you plug in ck, right, in cosine form, we would have vt over t0 summation going from 1 to infinity for vt over t0 absolute sinc of k omega 0 t over 2, right? And cosine of k omega 0 t plus the phase of ck in absolute values. The reason that I have to put in absolute symbols here is because we are taking the magnitude of ck. So when ck is negative, we have to take in only the positive part. So that's why I have to put the whole thing inside of the absolute notation. And if we unfold it, we would see that it would look like Vt over T0 cosine of 0, right? Plus 4 Vt over T0. Actually, just 2. not 4, sorry, 2, 2, an absolute sinc of k omega 0 t over 2 and cosine of omega 0 t plus the phase of C1, okay, plus 2 Vt over T0 absolute sinc to, sorry, to omega 0 t over 2 and then cosine of 2 omega 0 t plus the phase of C2 and so on. Now we have only positive frequencies. Okay, this is at 0 frequency, right? This is at frequency 0. So this is the component of xt at frequency 0. This is the component of xt at frequency omega 0, which is the fundamental frequency. Okay, this is the omega 0 is the frequency of xt, right? So this is the first harmonic, which is the fundamental frequency. So this is the component of it, the amplitude of it, magnitude of it, as well as the phase. And this is the component at 2 times omega 0. Okay, two fundamental frequencies, and as well as the phase, and so on. And now we can plot it. Okay, we can plot it to have a one-sided frequency spectrum where only positive frequencies are considered. Okay, so this is at 0. This is at omega 0, 2 omega 0, 3 omega 0, 4 omega 0, 5 omega 0, and so on. Okay, and then the trick is, again, plot the sinc function. I'm going to plot the sinc function, but now, but now we don't have negative values because of the absolute here. So whenever the sinc goes under, okay, we have to reverse it and flip it to be over, right? Only positive values are considered because of the absolute notation there. So I have this. See? Normally this one would have to go under, right? Because of the sinc, but because we have the absolute here, we only consider only the positive value, so we have to split it up so that it becomes positive value, right? And then we plug in omega 0 there, okay, the first one, which is this value, right, this value, and plot it here. Okay, that is that value, it is that frequency, and at omega equal to 0, it would be Vt over T0, so this value goes here, and this value is that guy, and this is at 2 omega 0, so it goes here, this is that. You understand it, right? So I will have this one as C0. Okay, this is C1. This is C2, C3, C4, C5, and so on. C0 to C1, to C2, to C3, and so on. All right? And this graph is the one-sided frequency spectrum of our signal. You see the resemblance between the two. Look at the resemblance. Okay, the one on the top is two-sided. The one on the bottom is one-sided. Only the positive frequencies are considered. See, it's like the two-sided is here, right? When you're going to plot one-sided, it's like you're folding. This is the two-sided frequency spectrum, right? So when we want to plot one-sided, you kind of fold it to be only the positive. So when you fold it, Okay, the magnitude becomes twice of the two-sided because you have to add them together and you get twice the value. Except at omega equal to zero because there's just one of the value here. Omega zero is not twice. It's just one one value where it is not. This is just zero. So I think I have to write it down. Half of this. Actually, this one should go half the value. Here. The reason why it is half is because we multiply 2 for all of them except at peak C0. This is the only one where there is no factor 2. So that's why this is one. The height of this one is exactly the same as in two-sided, which is just magnitude of C0. Now, as for the phase, sometimes we need to know the phase here. The phase, we need to plot the phase sometimes. So when we plot the phase, the phase of CK for this particular signal, okay, if you want to look at the phase, we can look at CK over here. You see, whenever CK is positive, it is a real number, right? And we know that positive real number has a phase of 0. And whenever CK is negative, it is a negative real number, and we know that negative real numbers have phase of pi, right? The phase of this value is pi because it is a negative real number. So the phase of CK will go 0, pi, 0, pi, ultimately. Okay, so we have zero, and then pi, and then zero, right? You see, this lobe over this interval, ck, the sinc function is positive, right? So the phase of the sinc function is 0. Over this interval, the value of the sinc is negative, so the phase of the sinc is pi, right? Over this interval, the value of the sinc is positive again, so the phase is 0 again. So at frequency 0, the phase would be 0, right? This is 0, 0, 0, and at for omega 0, the phase is pi because the value of the sinc is negative, so the phase of it is pi, and so on, right? So this is pi, or 180 degrees. So this is called the magnitude, one-sided magnitude spectrum. And this is one-sided phase spectrum. Okay? All right. Are you with me? Are you guys with me? Sorry. Now let's look at another example. Are you done with this? For those of you who just came in, please take a look at the board. The room next Tuesday is not this room. We have to take a different room because this room is too small. It is too crowded, too small to be an exam room. And the building is number 3, which is the building next to this building, which is adjacent to this building. Go up half the story, and the room is 3204. Okay. It is on the right wing of the building, I think. The right wing of the building. If you have trouble finding it, please find it before the exam starts. I don't want you to get lost. All right, so next example. This one, I'm going to give you the signal xt equal to, let's see, 5 sine squared 1000 pi t. Okay, I'm going to ask you to find the Fourier series of x. Okay, B plot the one-sided frequency spectrum and C find the DC component. So what do you think? Can you do this? This is actually a tricky question. Now, let me ask you, how would you find CK for this signal? How would you find CK? To find the Fourier series, you have to find CK, right? You may want to start with finding CK. Don't copy my writing yet. Okay? Please take a look, because I'm gonna erase it pretty soon. Now, how would you find CK? If you use the formula here, CK equal to 1 over T0 integrating over one period, right? And that is xt e to the negative jk omega 0 t dt. First of all, you need to find the fundamental frequency, which is the frequency of this signal. So the first question is, what is the frequency, the fundamental frequency? What is the frequency of this signal? Is it periodic actually? Is it periodic? It is periodic. So because if we know that it is periodic, what is its period? Can you find the period of the signal? If you cannot find the omega 0, then you cannot use this formula, right? Yeah? Because to use this one, you have to be able to integrate over one period. And if you don't know the period, how would you be able to integrate? Now, hypothetically, if we assume that we know the period, suppose we know the period. Now, let's do this. If we know the period, then we'd have to integrate from 0 to t0, right? And then 5 sine squared 1000 pi t, okay, e to the negative jk omega 0 t dt. Now, ask yourself, can you do this integration? It's almost impossible to do this integration, right?
Well, it is doable. Actually, we can do it, but it is not worth the time. So if you want to find ck by simply integrating using the formula, you get stuck here. First, you won't know the period. If you don't know the period, you won't be able to integrate. Second, even if you know the period, how would you go about integrating this one? So in this case, we should not find ck using the formula here. So we have to go around it. So what do you think? What should be a better approach to finding ck? So I'm gonna erase this one, and I'm gonna have to take a look at the signal xk. Okay, I have to take a look at sine square, and I'll need to use the trigonometric identities on sine square, right? So what do you know about sine square? What do we know? We know that cosine. Oh, sorry. We know that cosine of 2 theta is equal to what? 1 minus 2 sine square theta, right? You know this. So that means from this identity, right, we have xt equal to 5 and then 1 minus cosine of 2000 pi t, right? And then divide by 2. Are you with me? I'm using this identity on the sine square there. So I got this. Follow? And then I have 2.5. Well, tell you what, let's change this to 6. Sorry, let's change this to 6. Okay, to make the numbers easier, let's change it to 6. Sorry about that. So when we have 6, we have 3 here, and we have minus 3 cosine of 2000 pi t here. So do you see something now? Can you see anything? Now I'm gonna use Euler, right? Euler, e to the j theta equal to cosine theta plus j sine theta. So from this we have cosine theta equal to e to the j theta plus e to the minus j theta over 2. Okay, so I'm using this on the cosine term there, so I'm gonna get 3 minus 1.5. I should have changed it to 8. 1.5 e to the j 2000 pi t. Okay, and minus 1.5 e to the minus j 2000 pi t. Now, can you see something? Again, actually, this is the Fourier series of xt. Can you see it? Can you see that this is actually the Fourier series? This is already the Fourier series. This is C0, right? This is C0. This is C1. This is C1. Omega 0 is this guy. This is the omega 0. This is C minus 1. Okay, this is minus omega 0. And the rest of the C's are 0. Okay, here, if you don't see it, I'm gonna write down Fourier series, right? We know the Fourier series is this complex exponential. Okay, and it is z0, right? Plus c minus 1
e to the minus j omega 0 t plus C1 e to the j omega 0 t plus C minus 2 e to the minus j omega, minus 2 j omega 0 t plus C2 e to the j2 omega 0 t, and so on. So if you compare each term, you see that this is C0, right? This is C0. And this is C1. C1. Yeah, omega 0 is 2 pi, 2000 pi. This is this is C minus 1. I'm sorry, this is C1, this is C minus 1. C minus 1 here. And the rest is 0 because we don't have other terms here except these three terms. So C minus 2, C2, C minus 3, C3, and so on are all zeros except for C minus 1, C0, and C1. Okay? So from there we have C0 is 3, all right? C minus 1 is equal to C1, which is minus 1.5. 1.5 here. And then CK is 0 for K equal to plus minus 2, plus minus 3, plus minus 4, and so on. Are you with me? Do you understand it, right? Yeah. Look at this. What do you say? What do you say about the frequency? This is just cosine 2000 pi added by a constant, right? So the frequency is 2000 pi, right? If you don't believe me, you can plot it. You can always plot it. If you plot it, the graph will look like this. If you plot it, okay, this is xt. If you plot this signal, right, this function, the graph will look like this. Okay, and the magnitude, the amplitude is 3. Here, this is 0, and this is something here which is this is 1 millisecond. Yeah, 1 millisecond. So the fundamental frequency is 1000 hertz, which is 2000 pi radians per second, and the period is 10 to the negative 3. Okay. And so this example tells you that sometimes when you want to find CK, okay, especially for sinusoidal signals, right? There may be some other ways to do it, and maybe a lot easier than the direct approach. Okay, you have to maybe think outside of the box to find CK. All right. So this is already the first series, right? This is already the first series of the signal. Now we want to plot the one-sided frequency spectrum. Now let's do it in part B. Are you done with this? Can I? So this is the answer to part A. Okay, answer to part A here. This is already in Fourier series, a Fourier series. Now for part B, all right, we want to plot a one-sided frequency spectrum, right? So we see in this case all the C's are real numbers. Okay, all the C's are real numbers. So it is quite easy to plot the frequency spectrum. One-sided, I mean, 2 absolute CK, right? Now, at omega 0, at omega 2000 pi, right? At omega 4000 pi, at omega 6000 pi, and so on, and 8000 pi. Okay, now C0 is at omega equal to 0, right? This is C0. Okay, C0 is 3. C0 is 3. So we have 3 here. This is 3. Okay, C0. Look here. C0 is 3. What about C1? C1 is also 3, right? This is C1. You may think, hey, this is a negative sign here. There's a negative sign here. How come I say only 3, not negative 3? That's because we have to take the absolute value. We have to take the magnitude, right? So this is C1. C1 is also 3. This is 3. And for the rest, we don't have other C's, right? We don't have other C's. We have only these two terms. This is C0, this is C1, and the rest is 0. So I'm just going to mark it down as 0, and so on. And this graph indicates that this signal only has 2 frequencies. The first frequency is at 0, and the second frequency is at 2000 pi radians per second. Okay, now what about the phase? What about the phase? Now, if you look at the phase at omega 0, at omega equal to 0, the phase is 0, right? Because it is a positive value. This is a positive real value, so the phase is 0. Here. Okay, now what about the phase at omega 2000 pi? What do you think? The phase of this signal is what? Is it 0 or is it pi? It is pi, right? So how do I know it is pi? Because we have a negative sign here. Okay? The value, the phase, because it is negative pi, right? And we know that the cosine has to be added by pi. The angle has to be added by pi for it to become negative, right? So the phase is pi at 2000 pi. Okay? At frequency 2000 pi. All right, and for the rest, we don't have the rest of the terms. The rest of the terms are 0, so the phase of the rest is 0. Okay, so I have this and that. Right, this is 2000 pi, 3000 pi, 4000 pi. No, 4, 6. Sorry, 4, 6. 4, 6, 8000 pi. Okay, this is pi. Okay. What do you think? Okay, now better now. Now, as for part C, can you tell me what the DC component is? What is the DC component of this signal? It is, if you want to find the DC component, look at frequency 0, right? Because DC is at frequency 0. So it is 3
and the phase is 0, so it's positive 3. Alright?
That's it. Alright? Now let's do some more. One more. If I give you this, okay, let's say I'm giving you this spectrum. Okay, suppose I give you this magnitude spectrum, one-sided, of course, and as well as the phase. And I ask you to give me the Fourier series of this signal. Can you do that? Can you give me this signal here?
Can you fill in the blank here? If I ask you this, can you fill in the blank? Given this graph. Can you do it? Alright. Starting with k0, starting with k equal to 0, which is c naught, right? C0. The value of the magnitude is 2 and the phase is pi, so the value of C0 is minus 2, right?
So let's start with minus 2 here. Okay, this is C0, right? The minus side comes from the phase, which is pi. Now, C1.
The frequency of this signal is obviously 100 pi radians per second. Okay, the value of C1 has the magnitude of 1, and the phase is pi over 2.
So we have 1, okay, times cosine of 100 pi t plus pi over 2. Okay? Now,
the next frequency should be at 200 pi, right? But at this frequency, the magnitude is 0. So we don't need to write it down, okay, because it is 0. And the next one is at 300 pi radians per second. And the magnitude is 1, so I'm just going to write down another one.
The next one, which happens to be the last one, and the phase is of course pi over 2. Okay, we have only 3 terms here. Okay, so tell me, can you simplify this? What do you know about cosine of theta plus pi over 2? What is this? What is this value? Theta plus pi over 2. So it is cosine of pi over 2 minus theta, right? Okay, and it is sine of minus theta, right? Okay, so it is minus sine theta, right? And so if I want to simplify it, I'm going to have minus 2 minus sine 100 pi t and minus sine 300 pi t. So this is the signal we're looking for. Okay, this should be the one that we're looking for. All right. Okay, any question, please? Now, I would like to spend the last 20 minutes on some properties of Fourier series. Okay, we're going to talk just 3 properties. Okay, namely, the first property is called linearity. The second property is called time shift. And the third is amplitude transformation. Amplitude transformation. Now, let's look at linearity. Linearity goes like this. Suppose we have 2 signals. Okay, suppose x and y are both periodic with the same frequency. Okay, with the same period of frequencies. Okay, let's call it 2 pi over omega. And let Z to be a linear combination between x and y. Okay, where alpha and beta can be complex numbers. Okay, alpha and beta are complex constants. They can be complex numbers. They're not necessarily real numbers. Then ZT is also periodic, right? Periodic with the same period. And because it is periodic, right? We know that we can write it down as a Fourier series representation. And CK, okay, of Z would have to be alpha AK plus beta BK, where AK and BK are Fourier series coefficients of X and Y. respectively.
Right? So in other words, if you do a linear combination between two signals, if you do a linear combination between x and y, then the Fourier series coefficient of z will also be the linear combination, the same linear combination between the coefficients of x and y. This makes sense, right? So it is very useful. For example, if I give you this example, if I want to find the Fourier series of this signal, no, sorry. Um, let's say this is T1, okay, and this is T2, and this is T0, this is C. Now, if I ask you to find the Fourier series of Z here, how would you do it? You see something? This is 1, this is 2. Do you see something here? See, the signal X, okay, is very much related to rectangular pulse signal. You see, if you disregard, if you ignore this part for a while, you see that it becomes this signal, right? This is a rectangular signal, right? Rectangular signal. And on this, to this, you add another rectangular signal which goes like this. And you're gonna get Z. Okay, look at it again. You see this pulse, right? This pulse is composed of two rectangular pulses. The first one being this guy. Okay, and then you add to this guy another pulse here, and the result will become this pulse. Okay, so I can rewrite this as I'm gonna call this X. Okay, I'm gonna call this X, and X is this. This is X. Okay, this is X. Okay, this is X. And Y. Y is this. Okay. This is Y. Okay, and this should be 1.
It should be 1. This is y. This is y.
Now, if we add these two together, okay, meaning that we're putting y on top of x, right? We add them together, meaning that we're putting y on top of x. The result would be z. All right.
So we see that from this we notice that z is xt plus yt, right? And we know the Fourier series coefficient of x, right? Because it's rectangular pulse, right? Rectangular pulse train, and we know that rectangular pulse train has the Fourier series coefficient of what? Of this, right? So I'm just gonna copy this. I'm just gonna copy this. Okay. The Fourier series coefficient of x, we know it by a, right? By a. This is a. Okay, and v is 1. Okay, v is 1. T is t0. T is t2. So it is t2 here. All right. And what about the Fourier series coefficient of y? For y, the only thing that's different is t2, which should be changed to t1. Okay, this is for B. And then the Fourier series coefficient for Z is just AK and BK added together. Okay, by linearity. So we have CK would be AK, right? Plus BK. And that is T2 over T0 sinc of K omega 0 T2 over 2 plus T1 over T0 sinc K omega 0 T1 over 2. That's it.
And using this approach, you don't have to integrate whatsoever, right? You just take what you have already known and add together and do the linear combination. Okay? So this makes things a lot easier. This makes life easier a lot. You can be more imaginative of this. Okay? You can I could have made this go away, right? I could have, look at this. Look at my finger. I could have made Z like this. Go from here, right? And go up 1 and go down to 0 and go up again. I could have made it like this. If I did that, if I made it like this, how would you go about finding the CK? See, here, what we did was for this signal, right? Go to 1 and then go up again, 1 and then go down and then go down again. Now, if I changed it to this, go up 1 and go down to 0, and go up 1 and go down to 0. If I did that, then this equation has to be negative, right? I have to subtract y from x, right? If I did that. Now, look again. Another one. If instead of going this way, right? I go this way. Go up 1 and go down to -1. Okay? And go up to 1 again and go down 0. How would you change it?
let me draw it. Let me draw it. If I do this, go up one, right, and go down. Let's make it here. All right. Now, how would you do? How would you find ck? This is 1. This is not minus 3. So this would be ck equal to xt, right? Minus what? Xt is this guy, right? Going 1, right? Going up 1. This is t1, right? This is t2. Xt minus 4y, right? 4y. Because you have to go down 4 units, right? From 1 to negative 3 is going down 4. So ck must be ak minus 4 bk. That's it. So I think you really have to figure out this equation, right? Given this, you have to think, how would I relate this graph, okay, to the ones I already know, right? So you have to figure out what this one is to be able to use this equation, to be able to use this property. You have to figure out this, right? And you can be more creative, okay? Think about something else. All right, the next property is time shift. Time shift goes like this. If x is periodic with Fourier series coefficient, let's say ck, all right, then yt, which is x t minus t0, yt is x shifted by t0, all right, is periodic with Fourier series coefficient d, let's call it d, okay, to avoid confusion. D equal to ck e to the negative j k omega 0 t0. So in other words, if you do the time shift of a periodic signal, then the result will also be periodic signal, and you can find the Fourier series coefficient of the result by simply multiplying the Fourier series coefficient of x with a complex exponential, okay, where t0 here is the time shift here. The amount of time shift here will appear in this complex exponential here, and omega 0 is the frequency of the signal x. So as simple as that. And how would you use this one? Example. Actually, we can prove this quite easily, but we don't have enough time to do all of this. So let's just look at the example. If I give you this signal, can you find the Fourier series coefficient? Okay, if I give you this, can you find the Fourier series coefficient? Let's say this is 0, this is t, this is t0. Let's say this is 1. Can you find me the Fourier series coefficient of y? Can you do that? Oh, I just realized that it's already 12:15. So we see that this
if you look at this, what are you reminded of? We would think about a rectangular pulse, right? This looks very similar to a rectangular pulse, except that the original rectangular pulse that we found the Fourier series coefficient, our rectangular pulse is this one, which is symmetric about the y-axis, right? This is the original rectangular pulse that we defined, that we used to find the Fourier series coefficient. But the signal y in this example is not exactly this guy. It is this guy shifted to the right, right? If you shift it to the right by t over 2, if you shift it to the right by t over 2, you're gonna get this one. Okay, so I'm just gonna write this one. Oops. I'm just gonna write x here. Okay, x would be this. Okay, this is x, and this is t over 2 minus t over 2, and this is t0 here, and this is 1. And you see that y, you see that y is the signal x shifted to the right, right? So xt minus t over 2 shifted to the right. Okay, but ck for x is what? I don't remember. Sorry. ck for x, yeah, is t over t0 sinc of k omega 0 t over 2, right? This is a rectangular pulse coefficient, right? So dk for y would be t over t0 sinc of k omega 0 t over 2, and then e to the what? E to the negative jk omega 0 t, right? Yep. Here, we're shifting right, right? We shift right. Shift right means that we have to. And then divided by 2. That's it. Okay, that's it. Give me what, 5 more minutes, sorry. 5 more minutes and we're done. Amplitude transformation. I'm not gonna give you any example on this one because it's so easy. Okay. Let y, I'm gonna assume that x is periodic again. Okay, where x is periodic. Periodic with coefficient ck. Okay, then dk, actually, then d0, which is the Fourier series coefficient of y, right, would be alpha ck, and dk would be alpha ck plus beta are the Fourier series coefficient of yt. Now, this looks almost like a linearity, except that you have to be careful here. In this case, for amplitude transformation, For D0, you don't add beta to it. Okay, it's just alpha CK, which is the DC component, right? C0 here. C0. Because the DC component is already actually
it has to be the other way around. Sorry about that. Has to be the other way around. Yeah.
the DC component is the DC component of X multiplied by alpha plus beta. And as for the rest of the frequencies, you don't have to add beta to it because the beta itself is the DC component. So you add it to the DC, and you don't add the DC component to other frequencies. That's why the other frequencies, for other frequencies, you just multiply by alpha only. You don't have to add beta to it. Okay? So this is the amplitude transformation.
All right, and so we're done with this chapter.
Next Thursday will be Fourier transforms, and of course next Tuesday will be the exam. Okay?
2 hours you should be enough. If you cannot do the exam in 2 hours, then
I don't think you can do it in one day.
2 hours is enough, should be enough.
So see you on Tuesday at 10:30. The exam will start at 10:30, not 10:45. 10:30. Please come on time. And the room is 3204. Okay, please go locate the room first.
And bye-bye. And the problem set of the first series is already posted on the web attendance. Yeah, I know. On Google Classroom, as well as the solution to the class transforms and solution to first series will be posted within this week, right? Attendance. Mark B. Attendance. A B to the attendance.